Earlier we talked about a theoretical engine that would have the maximum possible efficiency. Here is a pragmatic approach at designing a theoretical engine that's based on a frictionless piston and a working fluid that exchanges heat with two thermal reservoirs. Thermal reservoir A, or 1, and 2 takes heat in, causes an expansion, and then dissipates the heat part of the cycle into the thermal reservoir 2. So the question is, what is the efficiency of an engine like this? So our goal, not our goat, our goal is to determine efficiency for an engine like this. What I have drawn here already, besides the device, is a pressure volume diagram and a temperature entropy diagram. And let's take one circuit around this diagram and understand what's going on. Let's start at point A. So point A, it starts right here at a high temperature, a low entropy, so a high T, a low S, and then it starts at a high pressure and a relatively a low volume, the lowest volume that you'll have for this device. So what's happening as we go from point A to point B around this circuit. Starting with the lowest volume and the highest pressure. So our piston will be in the phase where it's here, and the working fluid is right here. And what's happening is it's going from that phase, from that space, over to a situation where the working fluid volume is going to be substantially larger with a pressure that is lower. So we're going to go from that to that. And by having some device that attaches to this connecting rod to your piston, you're able to extract work from that process of the expansion as you go around the entire circuit. So the first stage, when we go from pressure at point A, the volume at point A, and temperature 1, to pressure at point B, volume at point B, we're still at temperature 1. So this is what we would consider an isothermal expansion. Isothermal in that it's staying at a constant temperature. Now to calculate maximum efficiency, let's suppose that this is reversible. We can also calculate the work done and the heat added at each stage of this. Okay, so the work done would be the integral from pressure volume work of volume A to volume B as this is expanding. And so during the first phase, at isothermal expansion from A to B at temperature 1, there has to be heat supplied from thermal reservoir 1 into this device. So the heat added at this stage would be Q1. That's step 1. What's happening in step 2? Step 2, the system is traversing from B to C. It's also changing from, I'm sorry, this should be a C over here and not a D. Okay, let's fix it. A, B, C, a D. This is going to be happening at a constant entropy, okay? And the temperature is changing from your T1 high temperature to T2 the lower temperature. So we're going to go from point pressure B, VB, T1 to another point. That's going to be at pressure C, VC, temperature 2. Okay. The process by which this is happening, it's isentropic. There's no change in entropy. So this is also reversible. And the process of the expansion, so it goes from a relatively high pressure to a low volume, at point C, at the same time that we have the temperature dropping. The temperature is dropping due to the expansion process. This is an adiabatic expansion. Adiabatic expansion. It's isentropic. There is zero heat flow, and the work being done is going to be minus VB to VC pressure dV. So that's step 1, step 2. Now what's happening in step 3? We are again going to be dumping heat at a constant temperature T2 into this next phase, into this thermal reservoir. And while this is happening, this volume is increasing and the pressure is modestly increasing. Entropy will be decreasing. So this is going to a smaller volume, so the molecules will be packed closer together, and the temperature will be constant, and the pressure will slightly increase. So this is a situation where you would expect the entropy to go down because your molecules are being pushed closer together. So on this diagram or table, we're going to go from PC, VC, temperature 2 through PD, VD, temperature 2. So isothermal, reversible compression. Reversible, isothermal compression. And the work that you're extracting from this process is the work you get by going from VC to VD, pressure volume work of PdV, and the energy that requires is Q2. We have one last step to complete our cycle. So to complete our cycle, we have to go from point D to point A on both pressure volume and temperature entropy diagrams. So we're going from this low temperature up back to the high temperature. We're going from the low pressure point D up to the high pressure point A to go back to the very beginning when we have our material in a very small volume that's highly compressed. So this is the cycle completion piece, PD, VD, T2 to PA, VA, to point PA, VA, T1, and this is a process of reversible adiabatic compression. So as this goes from VD to VA of PdV, and there's no heat transfer during this process of point D to point A. So in this way, the piston is going through all of the phases, and the working fluid is exchanging energy with the two thermal reservoirs. Let's look at the energy and entropy balance for this process. Here we have 0, because it's a complete cycle of the integrated form, equals the work you get plus Q1 plus Q2. So as we define work in this system, this is work done on the system, so we would expect this to be hopefully a negative value for work getting out of the system. 0 equals Q1 over T1 plus Q2 over T2. S gen goes to 0 because of all of the steps being reversible. Now we already made in our diagram all of the individual components for the work. What I have to do is sum them together. The work here that we extract from this process is the sum of all of those terms as we go around the cycle. So we go from volume A to volume B to volume C, and then volume C to volume D, and then volume D back to volume A of this whole cycle process. So what is the efficiency here? Well, solving for Q2, substituting Q2 in for Q2 of our energy balance equation gives us a relationship that we've seen before. So doing this process, this gives us minus W equals Q1 minus T2 over T1 times Q1 equals T1 minus T2 all divided by T1 times Q1. We've seen this before for our best possible engine. So the Carnot engine is, at least conceptually, one way that one could design a piston-driven engine to extract work from a thermal fluid, a working fluid, if you have all of the conditions of absolute no friction and everything else. So here the work that you expect is equal to the temperature difference between the two thermal reservoirs and the heat and transfer that you put in through Q1. But this is, again, an upper limit. It's a maximum theoretical efficiency for an engine. And so the Carnot engine is an example of the Carnot engine is an example of an engine you cannot make. But again, it serves as a starting point to understand cyclical processes for energy extraction in terms of work. Now, this is a thermal course for biomedical and ag and biological engineers. It'd be lovely to just keep going and talk about Otto, diesel, Rankine, and other types of engines, Brayton, but Stirling. But in this course, we're going to kind of limit it to the theoretical engines, and save that for mechanical engineering thermo, or maybe some future date of going through and looking at engines.